So to start this project, the first thing I needed to do was come up with a rotary unit that would have a motor compatible with the Shapeoko to plug it in. The original motor on my Shapeoko 4 is a NEMA 23 size 2.0 amp motor. So looking online, there's a lot of rotary units made for lasers that have a NEMA 17 motor, and they use rollers where you just set something on the roller. That's not going to work because a laser doesn't apply any pressure while it's doing its work, whereas obviously a C machine is digging in and pushing it around. So there's a few laser oriented units that have a chuck like this instead of just rollers, but a lot of them use a NEMA 17 motor because they don't need that much power again. And NEMA 17 motors come in a smaller amperage, so the problem is the controller on the Shapeoko wants to put out 2 amps, and if you put a NEMA 17 motor on there that's rated at 1.4 or 1.6 amps or something like that, it's going to burn it up because the motor can't handle it. On the other hand, if I go with a motor that can handle more amperage to some degree, that seems to be okay, because if I put, say, a NEMA 23 motor that's rated at 2.5 amps, which is what this motor is rated according to their website, the controller is only going to put out 2 amps. It's regulated, so it's not going to put out more than 2 amps. The motor obviously can handle 2 amps because it's rated at 2.5, and it'll be underdriving the motor, but just a little bit. The motor will still have plenty of power, especially given the fact that it's going from the motor to here with a 6-to-1 or 1-to-6 ratio. So really, the power, the torque applied here to the chuck is way more than they're ever going to need in order to do the work. So I chose this Vivor unit for that reason. 2.5 amp NEMA 23 motor I figured would be compatible, and through my testing it's been working just fine. So the next step, once picking a unit, is to figure out how to hook it up. Start with the original motor, and I had to figure out what the wires were doing. So a typical stepper motor used in a lot of this type of equipment, it uses 4 wires and it uses 2 coils. So there's 2 wires to hook up one coil and 2 wires to hook up the other coil. Well, which one of those wires is what? Because there's no documentation. Well, you just connect a multimeter in the resistance mode and you check between 2 wires. And if you get almost 0 ohms, you've found a pair that's connected to a coil. If you don't, then connect one of those wires to one of the other wires, see if you get 0 ohms, and then check between that one and another wire until you get near 0 ohms. Then you know you've found a pair. In this particular motor, the green and the black are a pair, and then the red and the blue are another pair. Once I've got that figured out, and you do the testing while it's not connected to the controller, by the way, then you just match up the colors, how they were connected through the connectors, the factory connectors that were on the Shapeoko, to the wires coming from the controller. And in this case, for some weird reason, the black wire from the controller went to the green on the motor, and the green from the controller went to the black on the motor. Then the white from the controller went to the red, and the red went to the blue. Go figure, right? Now that was the way I matched them up. Was the original, I'm grabbing the original connector, When I cut the connector off, I left a little bit of the wire on the connectors so that I could always match them up and know which wire from the motor went to which wire on the controller. So when make a good note of the wires before you cut the connector off, or like I did, cut the connector off with a little bit of wire so you can always reference it down the road. Once I've got this figured out, then I obviously cut the connector off, and then I hooked this terminal strip up, and I soldered instead of crimped these ring terminals on so that I can hook them up and then change them around. Eventually, I'm going to replace this with some quick disconnect plugs so that I can swap the original motor and the rotary motor when I want to do one or the other. I do the same thing with the motor on the Vivor. It did not say, they didn't have any documentation I could find. So again, I just used a multimeter to figure out which two colors were one pair and which two colors were the other pair. Now, they can go, you can't swap between pairs. So you don't ever want to have a wire from one coil swap to crossing over to one of the other coils. You want to make sure you keep these separate. But between each coil, these wires can be hooked up either way. So I could have the black one up here and the green one down here. Same thing with these two. All that happens is when you change them, the motor goes the opposite direction. I lucked out. I just hooked them up with the Vivor. I just hooked up one pair and the other pair and tested it, and it turned the direction I wanted to. So I didn't have to mess with that. But in your case, if you want to change the motor's direction, just change one of the pairs and swap the wires.
And here's a picture of the Vivor motor connected, so you can see that the black wire from the controller goes to black on the Vivor, green from the controller goes to blue on the Vivor, white on the controller goes to brown on the Vivor, and red on the controller goes to gray on the Vivor. So for calibration, the first thing we need to do is we need to figure out how far the machine says it's traveling in the Y direction when this does one perfect rotation. So what I've done is I have taped a piece of paper where I printed out a line every inch. I've taped that to the outside of this piece of pipe, and it does not matter really what the diameter of this pipe is, because for this part of it, all we're going to do is we're going to pick one of these lines and use it as a reference to do rotations, full rotations. So what I'm going to do is I'm going to jog the Y-axis. Until it stops, and then I'm going to go backwards to the nearest line, and I'm going to lower the Z. I've got a V bit in here, so it's got a nice sharp point at the end, and I'm going to jog that down nice and slow, and I'm going to rotate or jog the Y until I get that line directly under the V bit. So I'm jogging it in 1/1000ths at this point. Okay, and there it is. I'm going to set 0 for the Y. Increase my increment, raise the Z a little bit. And then I'm going to, I need to change this. By the way, for people who didn't realize this, the default in Carbide Motion is this says position, and this is relative to where you've set your zeros. But if you click on that, it actually says machine position, and this is the absolute position that the machine is at, regardless of where you set your zeros. So machine position, if you go to a particular spot, that spot will always be the same machine position. Anyway, so I go back to position. My Y is 0. I'm going to jog this. And what I want to do is, I could do this one rotation, get the V bit right on top of that line again, and then see what Carbide Motion says the travel distance was. But I've got room, my machine can rotate this 3 times at least, plus a little more, before it thinks that it's reached the front of the machine, or the back of the back of the machine, because it thinks it's close to the front at the moment, or at the front. So to get even more accuracy, if I rotate this thing around 3 times and then get that V bit on top of that line, read what it says the travel distance was, and divide that by 3, I'll get an even more accurate measurement than if I just did this once. Because if I just did it once and I'm off by, say, 0.04 of an inch just by eyeballing this, okay, when this travels 3 times around, it's off by 0.12 of an inch. But if I rotate this 3 times and I'm off by 0.04 of an inch, and then I divide it by 3 for one rotation, I'm actually off by 1 1/3 thousandths per inch. So I get a much more accurate reading. I don't know if that makes sense or not, but I'm going to rotate this around 3 times. So there's 1, 2, 3. I'm going to then jog this so that I get that line under the V-bit. Going to lower the V-bit again. Closer it is, the easier it is to read. Okay. Jog the Y some more. That looks dead on right there. So I've got a Y reading of 28.345. I'm going to open the calculator. And 28.345 divided by 3 is 9.448. So we want to remember that. This is for my specific setup. You could potentially buy the exact same rotary unit and get a slightly different number, maybe because some variation in the motor or slight variation in the pulleys or whatever. So you've got to do this on your own machine, regardless of what rotary you have, to come up with that number. But once you have that number, it's going to be good for that rotary to do this. And I'm going to show you what to do with that number when we come up with a specific piece of stock that we want to cut. So 9 .448 is my number. What we're going to do with that number is, if I didn't make this clear, the number 9.448 is when the machine thinks it's traveled 9.448 inches on the y-axis. This has rotated exactly one rotation. Okay. Well, the reason we need that is we're going to use that number. We're going to then, when you put something on here, you're going to figure out what the diameter of that piece of stock is, and we're going to compare that number with 9.448, and use that ratio to adjust a setting on the controller for the Shapeoko that controls the Y motor movement. Okay, now you can wrap your head around the idea of what's going on, or you can just plug the numbers in to do the math and make the adjustment, whether you understand the rest of it or not, because it took me a little bit to figure this out and wrap my head around how to make this work. So for this little example, I'm going to take that piece of PVC that I've been playing with and cut a test on it. And so I measured that to be 2.380 inches in diameter. So what we need to do is take that number, multiply it times pi to 4 decimal places, which will be accurate enough. I get 7.477 inches in diameter for that piece of PVC. So I'm going to go into Carbide Create, setup. The width would be the length of the wood or pipe or whatever you're cutting in the actual measurement. The height, however, is going to be that number, which I forgot, 7.477. So 7.477. Okay. So this represents, imagine if you took that pipe, the surface of that pipe, and unwrapped it and laid it out flat. That's what we're looking at here. Okay. So this would be the bottom left on this flat sheet is going to be equivalent to a particular spot on that pipe. But one perfect rotation is going to end up here. Okay? So imagine taking this and wrapping it around the pipe after we're done designing this and then cutting it as a design. So let's do that. Let's do something here. I'm going to take, I'll make this one. I'm going to put this on here. And then we'll do another one. And another one. Whoop. Oh, let's get done with that. Move this around like that. So this is going to cut on part of, less than half the diameter of that piece of PVC. I could keep going here, right? Let's do some more. Let's see here. Okay. One thing to keep in mind, if I group that and then I align it to stock, like so. Okay, one thing to keep in mind is the gap. Keep in mind it's gonna, from the starting from 0, it's gonna have this gap here. And then when it's done, it's gonna have this gap here. And keep in mind this gap is going to be next to this gap because the beginning is the end and the end is the same as the beginning. So this gap and this gap are going to be together and create an even bigger gap. So you need to space things out if you want, if this matters, so that you have half. Let's say I spaced these out so that I wanted them even all around the whole thing. I would want to have half a gap up here and half a gap up here or down here that I used between each of these. Alright, so I'm going to take this and I'm going to move it over here, and then I'm going to go and create a V-curve. Use stock bottom, always use stock bottom with a V-curve. 90 degree, I'm going to use a 90 degree V-bit. Okay. Save. Okay. There we have a file to run. Okay, so this step I'm going to show how you get through the initialization process and set zeros to get ready to run a file. I've got the machine off, so I'm going to go through a checklist here. The rotary motor is connected to the left motor connection coming from the controller. The right Y motor is disconnected. I have the bit setter is disabled since the machine can't move the gantry forward to reach it. I moved the gantry forward so that the bit is directly over the high point of the round stock. I've secured the gantry so that it can't move forward or backward when the rotary is rotating and pushing against the bit, so it'll stay in place. I have the rotary secured on my hybrid table. I have the stock mounted on the rotary, and I have adjusted it so that when the rotary is turning, there's no wobble, which is really important because if you've ever done a V-carve on a flat surface, quote unquote, that wasn't actually flat, and you had issues with the V-carve being inconsistent, the same thing can happen on the rotary. So you want to make sure that this stays nice and not wobbly while it's rotating around. So we're ready to go. What I'm going to do is turn the machine on. And when I connect the cutter, when I initialize, it's going to be able to initialize Z. It's going to be able to initialize X, but it's not going to be able to initialize Y. So what I'm going to do is I'm going to reach back there and I'm going to hold this wrench over the Y sensor to make it think it got back there, but I'm not going to be able to duplicate the actual process of what it would do to home the Y. And it doesn't matter because we're going to virtually home it after it fails. And you'll see that here in a second. So I've got the wrench over the Y homing sensor. And my recording software is not picking it up, but I've got an error that says HM008, the machine cannot pull off the homing switches. So I'm going to click on OK. Then I'm going to go up to MDI, and I'm going to type G28.3. That will virtually home the machine. I'm going to go to jog. And you can see over here machine position, not the regular position, but the machine position all shows normal as if it had homed at near zero. But only the X and the Z are correct. The Y, the machine's nowhere near the back of the table where it thinks it is. So I'm going to jog the X over. And I'm going to position it where I want my X0 to be. Remember, I've manually moved the gantry to get to the Y0. Excuse me, I've moved the gantry to position the bit directly over the highest part of the stock. To set the Y0, what I need to do is pretend like I'm jogging the machine forward towards the front. So I'm going to press and hold the Y minus and let it run until it stops. Okay, and then if you need to position it somewhere, if you want your Y0 to be somewhere on a specific part of the stock, as far as around it, you can jog backwards a little bit until you get to that point. When you do, then the next thing is we want to set 0 on the Z, so I'm going to use the paper method. That's pretty close right there. So fine tune that. Right there, that is catching on the paper. So I'm going to go to set 0. I've got my X set where I want it, so I'm going to 0 that. I've got the Y set where I want it, and I've got my Z where I want it. So they're all going to be zeroed at that location. And that's it. Now we're ready to run. So here's where we need to adjust a setting on the controller from within Carbide Motion to compensate for the diameter, the actual diameter of the stock that we're cutting. Okay? The golden number that I came up with earlier divided by the diameter of the actual stock, the circumference of the stock we're going to be cutting. So the diameter was 2.38. We're going to multiply that times pi. To 4 decimal places is plenty. 7. 7.477. Okay, so we're going to take 9.448 divided by 7.477. I'm going to type that out. 9.448 divided by 7.477 equals 1.264. I'm going to round it up to 3 decimal places. Okay, now that we have that number, I'm going to set that aside so we can see this. We're going to go into the MDI. I'm going to show the log window. I'm going to do double $sign to dump out the settings in the log window. Looking for $101 is 40. That's the default on my machine. So we're going to take 1.264 times 40 equals, and I've lost my calculator. There it is. Whoop. Where'd it go? It doesn't want to show up. Oh, it showed up on the other window. Sorry. Okay. $1.264 times 40 equals 50.56. So in Carbide Motion, we're going to go back to the MDI. We're going to type $101, which is an adjustment for the Y motor travel, equals that number, 50.56. Then I'm going to go back and do another double $sign to dump out the settings and make sure that that number is in there, which it is. 101 is 50.56. Now here's where you got to be careful. If you accidentally type something other than 101, you can mess up your machine. And you would need to go through the new machine setup wizard in Carbide Motion and download the settings once you've selected your machine and everything to push out the default factory settings back to the controller and start over. But be very careful. This is part of the risk of doing this. Okay, so that is set correctly. Now we can run the file. I'm going to load it. And I'm going to look at the previews. So the top view, text is all here. My 0 is down there. That's all relative to where I'm expecting. Front view, all these reds are rapids, the greens are cuts. They're just below the surface. That's what I'm expecting. Start the job. Okay, I'm going to mute my microphone while this is running, and I'll come back when it's done. Okay, that's done. When I hit OK, then it acts like it's moving to the back of the machine. There we go.